In our last video, we reviewed some basic information about compounds. We talked about the octet rule and looked at some examples of ionic bonds. And in this video, we're going to take a look at covalent bonds. In our previous video, we looked at examples such as sodium fluoride and magnesium chloride. Here is another example, F2. The electron configuration of fluorine is 1s2, 2s2, 2p5. So we know that fluorine can gain one electron to form F minus, and in that way it becomes like a noble gas. But if we were to have an ionic bond, we would also need to have a cation, but that would mean that fluorine would have to lose 7 electrons to become fluorine plus 7. That is not going to happen. So ionic bonds are not always going to be feasible. Ionic bonds work when you have a metal and a nonmetal. The metal can become a cation, the nonmetal can become an anion. But when we have two nonmetals, whether they're the same element or whether it's different elements, if they're both nonmetals, then ionic bonding doesn't work, and instead they're going to be held together by covalent bonding. Now, covalent bonding involves sharing electrons. Covalent bonding occurs between a nonmetal and a nonmetal, and the attraction, what actually holds the atoms together, is the attraction between those shared electrons and two nuclei. When we write covalent compounds, as we're thinking about covalent bonds, we want to use Lewis dot structures. And we use the Lewis dot structures to represent the valence electrons. For fluorine, we know that it has 7 valence electrons, so we can write a pair and another pair and another pair and a single electron. And now we have another fluorine atom, again with our 7 valence electrons. And as we think about a covalent bond, we can imagine that these electrons are being shared. As we write a molecule, we can write it like this, where these are the electrons that are shared. But it's more common to write a covalent compound using a line to represent the two shared electrons. So I encourage you to think about a shared pair as a pair of electrons, but we're going to write it as a line which represents a shared pair of electrons. Keep in mind, with ionic bonding, we are not talking about shared electrons, so we will not use a line in between sodium and chloride, for example. But we use the line between the fluorine atoms because this line represents a pair of shared electrons. Also, in contrast to what we saw with sodium fluoride and other ionic compounds, rather than having a network of interactions, what we have is a specific bond, and therefore we have a distinct molecule of F2. Why do we need to care about covalent bonds? Well, organic chemistry is the chemistry of carbon, and carbon has 4 valence electrons. So it'll be pretty unlikely for carbon to form a 4 plus cation or a 4 minus anion, and so sharing electrons, covalent bonds, are going to be very, very important in organic chemistry. Let's consider a few more examples of covalent bonds. The Lewis dot structure for carbon shows 4 electrons because carbon has 4 valence electrons. Hydrogen has 1 valence electron, so we have a single dot representing that 1 electron. And these electrons can be shared, so the carbon can share 1 electron and the hydrogen can share 1 electron, forming a single carbon-hydrogen bond. Now, I'm only focusing on the bond, not the entire molecule, so we still have these other electrons that we would have to worry about, but right now I'm just focusing on this. So we can have a covalent bond between carbon and hydrogen. In addition, we could have carbon sharing an electron with another carbon, which is going to give us a carbon-carbon single bond. It's also possible that carbon could share a pair of electrons, and another pair of electrons. And that would give us a carbon-carbon double bond. And finally, we can have carbon share one pair, two pairs, three pairs of electrons, giving us a carbon-carbon triple bond. So here we have just a portion of a molecule, but as we're talking about covalent bonds, we can already see a variety of bonding possibilities. An important characteristic of a covalent bond is that the two atoms involved in a covalent bond share electrons. If they share one pair of electrons, you have a single bond. If they share two pairs of electrons, you have a double bond. If they share three pairs of electrons, you have a triple bond. But although they share electrons, they do not necessarily share them equally. Elements have a characteristic called electronegativity, and this is a measure of the ability of an atom to attract electrons. So while it's sharing electrons in a covalent bond, different elements have different abilities to attract those electrons. So really we can think of electronegativity as greediness. Here we have a periodic table that shows the electronegativity values, and we can see that the highest electronegativity is up at the top right of the periodic table. So fluorine is the most electronegative element, and then the electronegativity or the greediness toward electrons decreases as we go down and toward the left. What I want you to keep in mind in terms of relative electronegativity, I want you to remember Falkland-Birch. So fluorine is more electronegative than oxygen, is more electronegative than chlorine, is more electronegative than nitrogen. Falkland. Nitrogen is more electronegative than bromine, which is more electronegative than carbon, which is about the same, just a little bit more electronegative than hydrogen. So Falkland-Birch gives you the relative electronegativity that I want you to keep in mind. This is going to be very helpful as we are considering a lot of different types of organic compounds. Now let's look more closely at a couple of covalent compounds. So here we have fluorine, F2. Fluorine is the most electronegative, but both of them are equally greedy, and so they have to share equally. On the other hand, if we look at HF, fluorine is much more electronegative than hydrogen. So although this represents a pair of shared electrons, those electrons are not shared equally. Because these electrons are not shared equally, this leads to a dipole in the molecule. We can represent that dipole by pointing toward the atom that is more electronegative, and then we cross the arrow on the side that is less electronegative. Please keep in mind this is different from the way dipoles are indicated in physics textbooks and in some general chemistry textbooks. So in some of those, they are going to show the dipole going in this direction, but it's a different type of notation. So I want you to be aware of this different convention. For organic chemistry, we are going to use this to indicate a bond dipole. And what I want you to remember is you point toward the electronegative element, and this leaves you behind with a plus on the other atom. Another way that we can represent HF to be able to demonstrate the bond dipole is writing it as HF. We can indicate that there is a partial negative charge on the fluorine and a partial positive charge on the hydrogen. So this is the Greek letter delta, and it stands for a partial negative. So fluorine is not F minus the way that it is in an ionic bond. Hydrogen is not H plus, but hydrogen has partial positive charge, fluorine has partial negative charge. What we have here is an electrostatic potential map of HF. So here we have the solid and here we have it as the cutaway so we can see what's going on. So this represents hydrogen and this is fluorine, and this represents the cloud of electrons that are shared between the hydrogen and the fluorine. Now the shape and size reflects the fact that we have a small hydrogen atom and a larger fluorine atom, but the color indicates the relative charge. So with electrostatic potential maps, blue is positive character and red is negative character. So we can see that the hydrogen side is more blue, so there is some positive character. The fluorine side is more red, so there is some negative character. Notice I'm saying character, so it's not a full positive charge, a full negative charge, but it's positive character and negative character. So covalent bonds involves sharing of electrons, but they are not necessarily shared equally. When these electrons are shared unequally, then this results in a bond dipole. Now, I want you to be able to make important distinctions and comparisons with different types of bonds. If we think about polar covalent bonds versus nonpolar covalent bonds, in both cases, we are talking about shared electrons, but the difference is that with a polar covalent bond, they are not shared equally, and so this results in a bond dipole, which can be indicated by a crossed arrow, or it can be indicated using the partial plus and partial minus designation. In a nonpolar covalent bond, those electrons are shared equally. Now, how does a polar covalent bond compare to an ionic bond? So, for example, a polar covalent bond, we might be talking about HF, and an ionic bond, we might be talking about sodium fluoride. So here we use the line that tells us that we have a shared pair of electrons, but we know that they are shared unevenly, so it results in partial charges. Our bond dipole gives us partial charges. So that our hydrogen has a partial plus, our fluorine has a partial minus. Contrast that with sodium fluoride, where sodium has a full positive charge and fluorine has a full negative charge. Another difference between polar covalent bonds and ionic bonds is that with the covalent bonds, this gives us a distinct molecule, whereas with sodium fluoride, this is where we have a whole network of attraction. And so that network is both within and between what we think of as molecules, whereas in the case of HF, that covalent bond is only within the molecule. There are different types of forces between the molecules, and we'll talk about those a little bit later. Often it's important to think about the strength of the dipole in a polar covalent bond. So once again, I want you to remember Falkland-Birch. And let's think about this. If we have HF, we have hydrogen and fluorine, and these are very far apart from each other, so a really big difference in electronegativity. So let's indicate that with a big dipole arrow. And then in comparison, HBr, there is still a difference in electronegativity. Bromine is more electronegative than the hydrogen, and so there will be a dipole, but it will be a smaller dipole than what we have in the case of HF. Another way that I could try to represent this difference is that with HF, we would have a big partial plus and a big partial minus, whereas HBr, we would have a smaller partial plus and a smaller partial minus. Now, please be careful thinking about the size of the arrow or the size of the delta plus, delta minus. You want to make sure that the difference in size is not just an accident of how I happen to write it. All right, in this case, I'm trying to be deliberate about showing that here there's a very unequal sharing, and here it's just a kind of unequal sharing. Okay, next, if we're considering HC versus OC, hydrogen and carbon. Carbon is just a little bit more electronegative than hydrogen, so this gives us a very small dipole, whereas oxygen is much more electronegative than carbon, so this gives us a bigger dipole in the other direction. And then finally, if we look at FBr versus FCl, F compared to Br, fluorine is much more electronegative. So here we're going to have a significant dipole, whereas F compared to Cl, fluorine is the most electronegative, but chlorine is still pretty electronegative as well. So it's not going to let fluorine steal as much electron density. So here we're going to have a smaller dipole. Now, as I'm talking about the strength of the dipole, the big difference is in terms of the difference in electronegativity. There is also a difference in terms of the distance. So in some cases, there are more subtle factors that contribute to the strength of a bond dipole. But in general, just thinking about the relative electronegativity is going to be sufficient for us to consider relative strength of bond dipoles. So let's summarize our brief review of compounds. With the octet rule, we want to remember that every atom wants to be like a noble gas, and many atoms, the ones that we're going to focus on, obey the octet rule because they want to have 8 valence electrons to become like a noble gas. And the octet rule, or really the desire to be like a noble gas, this is the driving force behind bonding. With ionic bonds, we are talking about the transfer of electrons. The actual bond occurs because of the attraction between a positive charge and a negative charge. And ionic bonds occur between a nonmetal and a metal. Covalent bonds, here we are talking about a sharing of electrons. The bond is because of the attraction between the shared electron and the 2 nuclei. Covalent bonds occur between a nonmetal and another nonmetal. When it comes to covalent bonds, in particular, if we're thinking about carbon-carbon bonds, for example, we can have single, double, or triple bonds. And it's also important to remember that a covalent bond could be a polar covalent bond. If there is a difference in electronegativity between the 2 atoms in a bond, then although those electrons are shared, they won't be shared equally, and this will result in a partial positive and partial negative charge. So this takes care of our review of some of the important aspects of compounds.